plastic to fuel, e-waste pyrolysis, and coal to methanol conversion. A fellow of multiple national and international academies, including the INAE, NASI, and the Royal Society of Chemistry, Professor Pant continues to advance India's energy security and sustainability through innovation, scale-up, and technology transfer. With this brief introduction, I first call upon my younger colleague, Dr. Sana Khanum, to present a bouquet to Professor Pant. Okay. Now please welcome Professor Pant for this year's distinguished lecture.
So very good morning to all of you, and thank you very much for inviting me here. Thank you, Professor Naveen. Thank you, Professor Shankar. Thank you all the faculty members of the department for providing me the opportunity to be here in front of all of you. And before going for the lecture, which is very, very general lecture, I would like to thank Honorable Mr. Jeet 𝗔𝗯𝘀𝘁𝗿 for bestowing this distinguished lecture series to IIT Kanpur, and it's an honor for me that I am standing in front of all of you because of him here and delivering this talk. So thank you, Mr. Jeet 𝗔𝗀𝘀𝘁𝗿, and his achievements are already well known, and I remember Professor 𝗁𝗁𝘁𝗁, who had been my advisor, right, and graduated from here during 1968, and had been the Chevron chair professor, which was also donated by him. I will just give this talk, if you look at the title, right, the energy scenario and industry perspectives, and especially for the younger generation, how can they move forward, right, from their PhDs to the next level, whether in industry or academia. That's more which is challenging for the future, if you look at the transformational research, because everybody is talking about the applied research, everybody is talking about the translational research and how it can be multidisciplinary, interdisciplinary. Those things are also becoming challenges, and especially for the young generation. You see that, right, what is happening, 𝗪𝗪𝗏, which has been, right, a term given by Honorable Prime Minister Modi ji also, and phase-wise, 1, 2, 3, 4, 5, and we are talking net zero by 2070, right? 3.4 million or gigaton, billion ton of the carbon dioxide which is coming every year in India, and if you look at world, 42, right, gigaton of the carbon dioxide. So everybody is talking net zero. The different countries have given the different kind of yardsticks that is to be managed in order to control this, and you see that 500 gigawatt out of this 1000 gigawatt should be renewable energy. Where from will it come, right? And we are talking green. How are you defining the green? That's again challenging, because you are talking solar energy. Is it really green? Wind energy, maybe green, nuclear energy, pink, right? Something, the different terms, words like hydrogen, right? Gray hydrogen to pink hydrogen, that has also been, right, given the terminology depending upon the carbon dioxide which is coming up from there, right? So this 𝗪𝗪𝗏 is very, very important, and you see that, right, the phase 2, right, which is 50% of this energy is to be supplied by renewable energy. 1000 gigawatt is the expected energy demand, and 500 gigawatt is to be achieved by this. Then the third phase, which is reduce the carbon emission by 1 billion, that is what we are saying, 1/3 of the carbon is to be reduced by this 2030. And then phase 5, which is very, very important, is that net zero. 2070 is quite far, but target is 2060, right? Because most of these developed countries, they are targeting 2050. So that is again, right, where we have to match with the world, right, how they are moving and how the science and technology, which is coming up in a big way in the country, that how can we bridge the gap. That is also very, very important if you really want to look at the, in terms of the developed country or from developing to a developed country. So that is very, very important. And this is what, right, the scenario. All of you know these things, right? So we are talking about a kind of $10 trillion economy. That is the developed country, right? Our developed country we are talking. So by 2030, that is the 10 trillion. Presently we are around $4 trillion. So the huge gap, right? 25 versus 30 in 5 years, you are saying that this $6 trillion, that is the additional, right, economy which is to be generated, and how will it happen? That's a very, very challenging, and lot of question marks are there whenever you talk about in terms of technology development, whenever you are talking in terms of the new, right, research which is to be carried out. 40% of this primary energy, which is around USD 90 billion every year, this is what we are importing, and we are saying that make it fossil free, right? So that's again a challenge, that what we will do if you don't import the crude oils, right? And that's again lot of issues when you, whether from Russia or US or some other Gulf countries, where from this crude oil is to be purchased at an economical price, that is again very, very, right, a question which is to be put, because politically there are a lot of changes across the world. So that is also coming. Per capita income, right? We are talking ourselves as a developed country, but if you look at the per capita income is just 0.6 ton. That is the consumption of energy, which is just connected with the developing, how developed we are. So 0.6 versus 1.8. So we are far behind. We need to bridge this gap, right? So when we talk about this, at least 2.5 times of the, right, we have to look at that our below poverty limit has to come up. And that's what, that every citizen of the country has to reach to a level where we can say that economy has grown up. And that's very, very important. And this is what the demand and supply, and then climate change, sustainability, providing the clean potable water, clean energy, and these are also integrated. Food, nutritious food, energy, and water. So this nexus is very, very important, because one thing if you want to increase, then other things may be disturbed. So climate change and sustainability and entire, right, when you talk about the balancing the ecology is very, very important and challenging. So this is what, right, I say that coal remains, right, because 55% is the share of the coal, or even 56%, and we are developing, we have to reduce the consumption of the fossil feedstock, but still, even in 2047, there will be the share of coal, and this is where I think we have to work that indigenous amount of coal, which is 240 billion ton of the coal which is available, but it is high in ash. So how you can design these kind of, right, your traditional living spill which you have read, there are different kind of fluidized bed gasifier, bubbling fluidized bed gasifier, entrant bed gasifier. What kind of gasifiers, right, would be good? And still it is debate, right, whether it should be just a gasification, oxy-steam, pyrolysis versus gasification, what combination, and there are a lot of challenges because it depends on the amount of ash which is present in the coal. 20% ash versus 40% ash with the Indian coal. So it may be something like where the entrant bed gasifier is good for low ash coal versus high ash. So something is to be done, or challenges which are to be addressed, and this is the small, right, what you see here, the power, 34% is the consumption of energy, industry 28%, and you see different, right, industrial, the sector wise, and the top, what you see by 2050 in terms of terawatt hour, different sectors have that. So renewable will come up, no doubt, in a big way, but if you see the contribution of the fossil derived feedstock, 11,750 terawatt hour out of this 10,000 terawatt hour which we are talking is the requirement of the energy, that's still from the fossil derived feedstock. So it means something is to be addressed, how the low carbon product can be derived, or how, if the carbon is high, how can you capture? So you know hydrogen to carbon ratio is to be kept high when you look at a clean fuel. So how to get that? That's again very, very important. And we need to work. So coal, I think still it will be dominating, and that's why the Ministry of Coal, Coal India Limited, or the government is still emphasizing on using this indigenous grade of coal effectively. So gasification or gasifier design is still a big challenge and pertinent point for the industry, whether you look at for power generation like NTPC, Thermax, all these, right, or the other refined petrochemicals, they are also using these grades for the hydrogen or different kind of chemical production. So there it needs a lot of work to be done in this area when you talk about, so 56% versus 36%, so still this is very, very, when you talk about 2 billion ton of coal which is being, right, consumed or will be consumed in future. This is the gap. You see today, 2050, right, when you talk about in terms of million tons per year of the productions when you talk about methanol, ammonia, plastic, and these will be the major products. And when you talk about plastic, huge amount of carbon, right? It is not, so net zero when we are talking about a carbon neutral plastic. Is it possible? This is what we are talking, the plastic where you are talking about high carbon to hydrogen ratio and you are talking carbon neutral, right? So what kind of feedstock are to be used? And methanol, right? Just I was discussing in the morning also, availability of methanol in India is a big challenge. And methanol is a very widely used chemical which is nowadays not only for the refinery petrochemicals purpose, but also for the vehicular fuel application also. So that's again, if you are using methanol for this automobile or ICE internal combustion engines, you need to find out the properties, right, in terms of application for the vehicular application as well as the quality at an economical price. Because if your methanol is not available at an economical price, there is no use of producing ethanol, rather imported from the China or other country. So this is also a big debate, right? The production within the country versus importing it from the other country. So you see that, right? Methanol, ammonia, plastic, and they are, right, widely consumable chemicals for the future, and all the demands which you see here in terms of how to bridge this gap. Because when you look at in terms of production of these kind of chemicals, the carbon dioxide which will come from these kind of products, you see that order of magnitude is reaching to a level of 4,000 million ton of carbon dioxide per year. So this is talking green versus producing carbon dioxide and adjusting the ratio of this carbon dioxide. So on an average, how can we reduce this number, say 100 gram, right, carbon dioxide per ton of the product versus less than 100. So that's where the lot of energy analysis, net energy rate, and lot of mass balance, process intensification, unit operation reduction. So these will be a kind of new concept for the future industry. Because reducing the unit operation will definitely your overall, when you talk about output or energy consumption in each process will reduce. So this is where we have to work at tabletop reactors, tabletop process design, simulate it, and then find out. So this is what you see carbon footprint, just an example for plastic emission, 3.5 gigaton per year, which we envisage by 2050 versus 1.4 in 2040. So this is the plastic consumption is increasing, right? Even we are talking banning the plastic, but plastic-based chemicals, 250 million ton carbon dioxide per year when you talk about the higher value chemicals from these kind of fossil derived feedstock and all these raw materials which are being derived for the petrochemical industry, but to talk olefins, right, or aromatics, whatever these are required for the future. So there is this last 4 bullet points are huge challenges which are to be addressed by refineries, petrochemical, fertilizer industry, steel industry, or any other pharma-based companies which are using these kind of chemicals. So what to do, right? This is what, right, everybody talks, right? What to do? We have to do something like that, right? The 2020, which is saying the hydrogen era, right? Everybody is talking since like last 5 years, green hydrogen or hydrogen, gray hydrogen, turquoise hydrogen, blue hydrogen. So those are the, right, from fossil derived feedstock. So even this turquoise hydrogen, which is produced from the fossil derived, just like methane decomposition, you convert it into hydrogen and the carbon nanotube. This is good area. Dry reforming, I know that, right, many professors work on that. Dry reforming, that can also be used, right, for syngas and then get water gas shift reaction and convert it into hydrogen. And biogas can be used for that purpose. So those kind of, it cannot fulfill the entire demand, but part of that kind of feedstock which would be greener, and this is what the government of India is putting a kind of mandate for all refineries, petrochemical industries, that at least 20% of the renewable component should be involved with this kind of fossil derived feedstock. So it means crude oil, add the bio-crude there, biomass, add bio-crude 20% of that and put it in the distillation unit. This is just one of the options which I am talking. Alternate can be also there. So we need to look at, right, for all these kind of, when the phasing out wood, coal and moving towards the natural gas or high hydrogen to carbon feedstock, which is the need for the future. And I think 2047 is far away, Viksit Bharat. But when we talk about, right, in terms of science, technology, research or academic units, I think it should be start, and already the zero that has been already started, and we have to find out that by what or where will we be in 2030, we need to work in these areas. You see that just traditional, right? You all study these things, right? Ranking cycles, combustion engines, right? You see the end point, right? Less than 20% efficiency when you use your gasoline, right? Diesel, 20% efficiency in everything. And individually what you see that, this is where we are, right? Whether it is the something in terms of e-vehicle, vehicular application, or for the industrial. So efficiency is very low. It means there are a lot of opportunities in between also if we can improve the efficiency, or we get rid of couple of these intermediate steps, right? So the removal of the intermediate, where we call one pot, right, tandem process, lot of things are to be done in that area, but this is something, right, where we are working just 30% efficiency, and overall efficiency for vehicles it's just 20%. That's why people move towards the fuel cell vehicles, right, reaching towards 60% efficiency, or better than those where you can reach the efficiency levels towards the 90 or 98%. I think that is the one thing, is that energy production and designing the system in such a way where the losses are at its minimal, and that is also very important to work on these traditionals, right, ranking cycles or ICE or maybe alternate vehicular applications. So this is where, right, the straight linear versus some kind of banding in between, right? So this is important in terms of the disruption potential. And when you talk about the technology readiness level, what actually the industry wants and what research is being done. So most of the time academic research is limited to TRL3, but I think there is a need that when the ideas are there, so ideas to innovation and investment, this is I think the younger generation now doing, startups which are coming up in a big way, and the concept of tinkering lab which is now being used. So when there are the ideas, right, and we have to work in such a way that can these ideas be taken to the next level. So a lot of these kind of, right, the maturity, when the ideas are there, we have to work on that and bring it towards the something like a maturity level, and that is where the TRL9 and then commercialization that is required, and this is where the lot of, right, you see that disruption versus scale, this is the confusion in terms of this. You might be able to suppress the disruptive development by scale for a certain, and that's why everybody gives the example of China, right, because they invest huge amount of, when they have the ideas, they invest the money, and sometimes the reverse engineering also being done by them, right. So reverse engineering is also accepted. You get some right product and then do whatever you want to do, open it and study it and then develop the new process, and that is also very important. I think government is allowing that kind of reverse engineering also, and we should work in those areas. And this is, I think, most of the time, most of the, you see even the industries like whether e-waste, metal extraction, the factories, the companies, right, from China, they buy the equipment, put it here. Okay, right. But now do reverse engineering in that and improve the efficiency and develop the product within the country, rather purchasing again and again from there. So I think that is also very important, that in future, what we have to do in terms of developing this, right, a kind of large maturity level from ideas to the product. So past, present and future. So future, of course, everybody is talking about green energy, right? But how much green, that will be a little bit questionable, right? But that's true that the coal, nobody likes, it's a black and dirty material. So coal, petroleum, natural gas, already, right? People are moving in that natural gas demand is increasing, and future will be somewhere where you talk about the hydrogen, biomass, biopolymers and all these things, right? Tissue engineering, healthcare, all these things are coming up using these kind of biomass-based products. So lignin, cellulose, and India has those kind of, right, the pulp and paper industry where these kind of materials are available, and that is where e-market is coming up, electro-based, right, where the methanol can be produced, plastic can be produced, so e-plastic, e-methanol. So that is again another terminology which has been given in terms of green energy. And for these, you need to do a lot of R&D, right? You have direct air capture, carbon storage, and then convert it into value-added products, that is utilized, point of source capture. So many things are there. All of you must be aware. The fossil energy system is to be replaced by the renewable energy system, and that is very important for the future. I'm not going in detail of this, but one thing is clear in this, that what you talk 3 tons per ton of the carbon dioxide which is being produced, they are the chemical produced, whatever the chemical. And when you talk about developed countries, you see that this point here, right, this is what we want target, which is below 90 gram, which I mentioned there, 90 gram carbon dioxide per kilowatt hour per unit. That should be the target when you talk about business as usual, which is 300, right, versus 90 gram carbon dioxide. This is where we have to adopt. And the last thing which you see, recycling, circular economy, that will bring to that level, right, versus biomass also to some extent. But if you talk just the carbon capture and utilize it, then the electric energy which is required, what would be the source of that electric? Means we are capturing carbon dioxide, converting into other product, but how much energy is required to convert carbon dioxide? You know, it is rigid thermodynamic molecule. It will require huge amount of hydrogen, and where from this hydrogen is coming is a question. So conversion of carbon dioxide to value-added product, although a lot of R&D is being done, but success story is not good. This is the fact. So this is where we have to catch the market for the future, that required carbon dioxide or CCUS. CCS may be easier because there you are not using hydrogen, but for CCU, although CCU is much more desired by the industry, process industry, but the challenge is there that you have to look at your business as usual, that is due to the electricity carbon footprint, because whatever the source of energy you are using for producing the hydrogen, and that is making this carbon dioxide conversion into fuels and chemical much more rigid and energy intensive process. And that is the last one where you have to look at, you have to work in those areas, and then you have to find out that 3 tons carbon dioxide per ton of chemical produced is to be reduced much below. So that's where the numbers are. Already the business, right, the US and some developed countries like France and Europe, they have achieved this model, 90 gram carbon dioxide. So below 100 is a good number. So this is what you see the pace with the refinery. When you talk about with the refinery, petrochemical, integrated approach, you say that your carbon feedstock transition, which is very important, and we have to find out the new kind of materials, raw materials at an economical price, sustainable economical price. That's very important. And then your pace of technology, because this is where the disruptions in between. So this is not a straight path. Disruption in terms of technological advancement, which is very competitive. Resource sufficiency, because sustainability is very, very important. We have to work on that. And economic and social viability, again, commitment toward the society. And this is where the challenges which are to be addressed, that AI-driven digital twin refinery. Data are available, right? And we have to study this real-time data analysis. And that is where I think lot of opportunities for the younger generation, those who are working for AI-assisted technologies and developing these kind of digital twin refinery for the future. And then some kind of process intensification like membrane-based process, because distillation process needs to be replaced. It is huge amount of energy consuming process. So if these can be replaced by low cost, more resistant membranes, I think that is also very, very important for the future. Circular and critical resource recovery, shift to high value niche to the specialty petrochemicals, and that is where I think the future is in terms of the refinery, and they are putting lot of pressure in that. You see that different type of emissions which are coming measured at S1, S2, S3, right? So S1 you see, that is a direct emission, refinery combustion, hydrotreater, cracker, steam methane, reforming, all these are emitting huge amount of carbon dioxide. Scope 2, where it is indirect energy emission. Again, it is electricity from grid, natural gas, crude oil, all this. Scope 3, which you see indirect energy emission, use of conventional fuel, road transport, industrial. So all these are contributing to the emissions in terms of carbon dioxide, and left-hand side is giving you the real picture. This is where the steam methane reforming, right? You see the products, ammonia, methanol, ethylene, propylene, aromatic, all these are very important products from the petrochemical or refinery. And every process you see the carbon emission per ton of carbon product, huge amount of carbon dioxide is coming. And if you look at in terms of capture, you have to invest the money. So this is where the future, where you see the fossil feedstock, you have to capture the carbon, that is the conversion approach. If you look at sequestration side, you have to look at unrestrained release of the carbon dioxide, capture and storage, and then finally thermal power generation, also the renewable power generation. Where from we will? This is just a speculation. And how can we work for these in terms of indirect energy related, direct energy related, process related. And again, there are a lot of challenges and opportunities for the future in terms of R&D, that every sector we have to do a carbon analysis, we have to do some kind of life cycle assessment, and then find out the process in terms of net energy rate which is required for a given process. So process intensification, right, what you call the traditional thermodynamic analysis, exergy analysis, these would be required for every process industry, and try to miniaturize the size of the refinery, tabletop refinery. So that should be, I think, a kind of concept for the future, and this can be done. There is just one example which I have kept here, right, because we work on this methane decomposition to hydrogen and carbon nanotube, and now working on biogas, right, methane decomposition, which can be called green hydrogen. So this is the challenges, right, and refinery is now addressing this, that steam methane reforming, what substitute can be done for traditional steam. You know now ammonia based, right, plasma reforming, plasma processed are also low temperature, non-destructive plasma. So those are where the reaction, typical Haber-Bosch process, right, for ammonia synthesis, which is done at 200 atmosphere, can be done at atmospheric pressure now, right. So this is where I think the trends have come, but how will you scale up those kind of reactors? That is again the very, very important for the future study. So non-thermal plasma for ammonia synthesis, for CO2 conversion reduction. So this is where just a typical example what you see, the energy consumption when you talk about steam methane reforming, which is 3 to 4 kilowatt hour per kg of hydrogen, versus when you talk about the carbon capture, it reached to a level of 45 kilowatt. Why one will do that, right? Because the consumption of energy has changed from 3 to 45. And if you go for water electrolysis, people are talking green hydrogen, right? But 55, this is the data, right, which is around 2022 to 45 and 49, that is the range for water electrolysis 15, 55. But methane pyrolysis is the advantage. You are getting the carbon as a solid, no need to capture, but only thing that the catalyst design, reactor design, these may be challenging. Different kind of heating approach can be done, and you can have a kind of turquoise hydrogen. So turquoise hydrogen is very close to blue hydrogen or green hydrogen. So that's what I think we need to work, that how to establish the existing technology which are already established, revamp them, or find out some ways, right, for improving the technology. So turquoise is something where a kind of, right, word. You see the complexity for the future refinery, right? All kind of feedstock, just not the fossil derived feedstock, but look at everything is there. You have the waste, MSW, use it there. You have the plastic waste, use it there. And several, right, renewable energy component like solar energy, wind energy, natural gas, biogas, crude oil. It means whatever you have, you use it in the refinery, and then you have to find out the design. You work for that, right? So versatile kind of feedstock, and then find out the methods, right, how it can be, whether it is a kind of, right, oxygen required, hydrogen required, where from these will come, and then you have a blue hydrogen, right, and this is where the directly integrate it with the petrochemical, because the gases which are coming can be integrated, and you can have e-fuels, you can have all green, and right, the ammonia which you call blue ammonia, calcium carbonates, right, and carbon dioxide. So whatever you have, that can be used for multiple. So this is where we talk zero waste, or you, right, as an academician must have read E factor rather, right? How much pollution you are creating when you are doing that. Because thermodynamics simply says that when you are converting A to B and A to C, if B is the desired, you try to work 100% B to that. Thermodynamically it may be difficult, but you have to work for that, right? You have to use some technique in between which can disturb your thermodynamics, right? So we have to talk about atom efficiency, and this is very important, that 99.9% should be your desired product. Otherwise, lot of energy is wasted, right, or for the suppression of the product. This is what the challenge. So something is to be done where your unit operations which are going on in the process can be minimized, and for that also lot of work is required. This is again, right, just an example. We are working on this. So gasification versus combustion, right? Both are right for power generation or maybe some kind of coal to methanol process. But you see that, right, in terms of the coal combustion, then you have to use the CCUS, then carbon dioxide or the products you have to sequestrate, and then coal combustion you have to work for the steam cycle. All of you know these things, power distribution. So if you look at the overall efficiency of the process, it's a very, very low. Second thing you see that, which is now coal gasification, right? So this may be a little bit, right, questionable also, but you have to do a complete energy analysis for both again, and now tools are available now. This is hydrogen or mineral, whatever you use for this gas cleanup, right, acid, gas, removal, all this. You have a power, you have a hydrogen, chemical. So this is, when you talk about the energy analysis, this is higher pathway and gives you the multiple product. So that's why I think combustion can be replaced by gasification, and this is what's shown here. 8 to 12% efficiency versus 48% efficiency. So this means analysis is required, unit operations at every sector, exergy analysis, and these are the new opportunities for design of a new unit for the future generation. So this is where, right, the gasification itself is a very, very costly affair. And when you talk about how a good gasifier, whether it is entrant bed or a bubbling fluidized bed, all of you have read this traditional Lewin spill. So how it can be done. So this is where I think the work which is required. So coal gasification has the option. Now you can do oxy-steam gasification, just partial oxy gasification or steam gasification. That is again, you have to understand with respect to the feedstock which is generally used, whether it is coal with different ash percent, biomass and multiple products. So this is just, right, because the work which we did with Thermax as a partner on coal to methanol, supported by Department of Science and Technology, and a notional plant of 1 ton methanol, right. So use just the high ash coal, 40% ash coal, right, and lignite based coals, right, and which are considered not good. So most of the thermal power plants, they blend the Indian coal with some high grade imported coal either from Australia or Israel, right, and then they gasify it. The reason is that gasification of the high ash coal has a lot of issue in terms of ash, clinker formation and the hydrodynamic study. Most of these things, right, whether it is oxy, what should be oxygen, what should be steam, these ratios are also very challenging, and that's why there are a lot of opportunities to study, and if these opportunities can be resolved, the issues can be resolved, then there are opportunities for the industries, right, or Ministry of Coal and financial support also in these areas. That is, so you see that gasification, and then carbon dioxide, you do some water gas shift reaction, that depends, right. You will have the, right, again carbon dioxide from there, acid gas removal unit, and all gases are removed, and finally, right, this is the CO2, and CO2 is again being sent into a reactor because we want to use the CO2 hydrogenation and producing the methanol in the single unit. So this is the second part of the Thermax project which you see on the upper part, but this coal to methanol 1 TPD, that is a notional plant working at Thermax, and this is the need that design of these kind of gasifiers which are still a challenge, because high pressure 10 bar pressure versus 5 bar pressure gasifier. So 10 bar pressure gasifiers are still not successful, 10 or 15, because higher the pressure you will have the advantage in terms of product distribution, but operational distribution like droplets will condense, will come down, thermodynamics, right, temperature pressure management. So these things are where the further studies are required in order to design these kind of units, and NTPC is doing, BHEL is doing, Thermax is also doing. So a lot of industries, they are still studying these kind of things. So this is, right, when you talk about need to integrate the coal, biomass, so we need to work in these areas, coal to gas liquids, then coal gasification, gas cleanup, because when you do this, you can convert coal to chemical, right, or coal to hydrogen. That's one the approach. It can be hydrothermal also, it can be slurry reactor also, or other kind of gasification. And when this is done, you can mix it with the biomass also, coal plus biomass, or must just convert biomass or municipal solid waste into RDF, refuse derived fuel, and mix it with the coal. This is what the now NTPC, they need 10,000 tons per day of this bio coal because the guidelines which have come up. So bio coal, which also very, very promising, you convert the biomass to bio coal by torrefaction, and this can be done, and then transport it, because you are increasing the density of the feedstock, right. So paral burning and all these things what you hear nearby Delhi, Punjab, Haryana, those can be resolved, and even in Uttar Pradesh also. Right? So again, this is a wider spectrum, right? Carbon dioxide from air, bioenergy, carbon capture, storage, fossil derived feedstock. You have to understand the chemistry of this, right? How much hydrogen would be required. Minerals are the critical minerals are very, very important, because if you use catalyst, then these are again a precious metal and challenges for the future. So spent catalyst metal recovery, convert them again into useful catalyst versus the minerals, extract the metal, because all these, whether it is energy storage materials, lithium, right, cobalt or manganese or graphite, carbon, these are very, very important. So integration is required. Process you have to select, right, different processes which have been given here. All processes have the pro and cons, and that is where we need to find out which process is the best. For one feedstock, it may not be the single process. You have to find out a most optimized process, and lot of things are still at infant level when you talk about the carbon conversion, because carbon conversion is not a good idea in terms of the energy consumption in the process. Availability of hydrogen is a big challenge at an economical price. So this is, I think, where a lot of work is required. This is what I said, right? Carbon dioxide plus hydrogen converted into methanol or dimethyl ether or any chemical, olefins, SAF, everything can be done. But this is where from hydrogen you get. So this is what the irony, 27 kg carbon dioxide if you use, just steam methane reforming, write down the reaction, around 13.5 it will come. Same thing with, right, different kind of feedstock, crude oil, right, where the hydrogen to carbon ratio is low. So this is where the number is approximately, and this is 12 to 13 kg when you talk about global average, because they have the processes which are well modified. The existing assets in terms of capture, which is 5 to 8 given, right, but need to work on 0.8 to 0.6. The Indian target, which you see here at this, 2 kg carbon dioxide per kg is accepted, green hydrogen, that is the MNRE guideline, right. So any process where you can say that the carbon dioxide emission is not more than 2 kg, that hydrogen can be considered as a green hydrogen, whereas other countries you see that the number is lower side, and we need to work. And of course the green you are saying zero hydrogen, zero energy, that is carbon dioxide, but that is practically difficult as of today. So we need to find out the ways. So hydrogen at an economical prices and green hydrogen which will not emit carbon dioxide, that's the challenge for the future, and that is again where the work is required. So this is where the Europe, right, green hydrogen through electrolysis, renewable power, which is growing 0 kg of carbon dioxide per kg of hydrogen. So this is where at an economical price, because cost will be very, very important for all these processes. So when you see the refinery trends, right, it is very, very now distributed, you see that, right. All products are being, same refinery, diesel, kerosene, and same refinery can produce the petrochemicals, methane, right, all kind of monomers, polymers, asphalt, and this is the, right, the concept for the refinery where you use the water, carbon dioxide, biomass, and a kind of green refinery they talk now, hydrogen refinery sometimes they talk. So different words, but this is where I think all these kind of processes are required for the future in terms of conversion and transformation of the product. This is what the, right, need of the hour. When you talk about e-methanol, I was talking about that, right. So all this pulp and paper industry, the India has potential of 20% of India's pulp and paper which can have the biogenic carbon. This is purest form of carbon dioxide. You need not to work any hard for separation, because coal gasification, the separation of the gases itself is a very tedious, because there is ammonia, there is carbonyl sulfide, hydrogen sulfide, so acid gas removal systems, all these things are very, very costly again. But this pulp and paper industries, or if you talk about the fermentation industry, that carbon dioxide is pure carbon dioxide. And that can be fermented, that can be used for different purpose, and that's why the number which you see e-methanol, those kind of words have come, right. This Lanjatech, you see that, right, they are setting up the, in Panipat they have the 200 TPD plant, although there are some issues, because enzymes and biotechnological route is another important, where the temperature, pressure, energy consumption is low. But the only thing that the conversion kinetics is very, very slow. So if you are looking something on the biotechnological approach, Then how to improve the kinetics and how can you make the process sustainable? That's very, very important. So thermochemical versus biochemical, that's where the lot of debates, right? So thermochemical, of course, the productivity is very high. Conversion is very high. You can control the thing. In biotechnology, if the enzymes in a better way, if can be designed, liquid phase catalysis, if this can be developed, because your mass transfer, diffusion resistance, traditional chemical engine problems, these resistances are there, and these should be kept at its low level. So solid base catalyst where the reactor height goes to 10 meter. If you have a liquid phase catalyst, your reactor height will go just 2-3 meters. Because your resistances are minimal. But how to control, how to separate the catalyst, all those things are very, very challenging. So these things are also to be addressed. So there is just a single step, but where we talk about tandem catalysis. Hydrogen you can get from the electrolysis, right? And then you can have hydrogen, methanol, water, right? If you react, you can have the right methanol, CO2 to methanol product, and that's again very important. CO2 to methanol, CO2 to dimethyl ether, CO2 to formic acid. You can convert in all, and but you see the water splitting versus right the single route process. Again, you can have a water splitting for hydrogen, but that affair is costly as of today. We need to find out the process by which water can be splitted electrochemically at a low route. So membrane design, all these things are very, very important, and that would be, I think, very important. So biogenic carbon dioxide, green hydrogen, and this e-methanol, 100 kiloton per annum of e-methanol, it has already been tendered with 23 Indian rupees per kg, that will be the cost, and the financing is around of the order of 220 crore for this kind of problem. So pulp and paper carbon dioxide, fermented based carbon dioxide, these can be converted into chemicals, and these are much greener chemical, and that is the electrochemical routes. You can talk on those processes. So, right, green hydrogen supplementation, because you have to integrate the carbon dioxide if you are talking the conversion and utilization, then this all factors are to be considered. This is what you see, investment which is required by 2030, 8 lakh crore, which will give you 10 million metric ton of the green hydrogen, and which is the huge amount of number, right, this hydrogen if you can produce, right, and hydrogen, green ammonia, and that's what the revenue which can be, right, saved in terms of the production. You see that if this is done, then the fossil import reduction, that is the target, is 50 million metric ton, right. So this is very important out of 94 million metric ton which is imported. So 50 million metric ton, and that will, right, a kind of 1 lakh crore revenue which can be saved. So these are two integrated approach, green hydrogen production, right, looking forward for that, and emission reduction target which have been given in terms of carbon dioxide by production, right, and emissions by 2030. So substantial scale up would be required if you look at 2030 opportunity, and that biomass gasification, right, water splitting, whatever, refinery intermediate, decarbonization. So these are just the steps where scope 1, scope 3, all these things can be done, right, 1, 2, 3, which I talked in terms of energy consumption. So, like all of you are talking about machine learning, artificial intelligence, DFT, these will play a big role, because without doing experiments, right, some theoretical studies would be required. And fortunately, the correct data, how to identify, right, these are available now, right. So we can select the correct data, do some theoretical analysis by doing some computational methods, and then look at that, right, what kind of, because characterization tools, all these things are also available, and then do the reactor design based on that, right, in terms of heating also, whether it is induction based heating, plasma based heating, or some microwave heatings, or whatever thermochemically, where from the energy will be coming, that's one thing important, right, and then how this can be made renewable, whether it is solar energy, hydro, wind, whatever, right. So renewable energy pathways you have to find out and do some catalysis, because catalysis can change the entire, right, domain of the spectrum of research. So green catalysis we talk nowadays, right. So the existing catalyst versus the novel catalyst, so there are a lot of opportunities in terms of developing the technologies, which can be in terms of liquid phase, which can be in terms of nanoparticles, single atom catalyst, those things are coming up, but how to synthesize and how to make them sustainable, right, adjust the tuning of this low cost materials, right, instead of using the traditional platinum group metals. So find out the ways, and then you have the plenty of opportunity in terms of this product formation. So machine learning in carbon neutrality, high throughput DFT calculation, molecular dynamics, dynamic challenge monitoring like in situ catalytic. So drift of brandy and all these in situ studies, all these right XANES, XAE, XFS, all these now high sophisticated tools are available for doing the research, and that is, I think, we should work. And then finally, when you talk about commercialization, life cycle assessment is important, techno-economical analysis is very, very important. So these things are also, because otherwise industry will not come forward. We have to satisfy the industry in terms of sustainability of the raw material, sustainability of the product, and finally the energy consumption in the process, and how much green is the process, that can be defined. This is also work which we are doing as of today. That's what the biomass, right? So you have the plenty of biomass, right? We have in total the biomass when you talk about 200 billion ton, right, which is available, and out of that 240 million ton is available all around the country. And this can be used effectively bio-based refinery. So low temperature versus high temperature. Both approaches are there. You can convert this biomass depending upon lignin, cellulose, hemicellulose into the fuel lubricants like furfural alcohols, right? The DMF, you can convert it into different kind of, right, chemicals, cellulose, right, low calorie sugar, so C5, C6 sugars, right. So those things can be converted, what you call total reducible sugar, and converted into different products, right, by understanding the right chemistry and catalysis, and this can be done low temperature. High temperature is something where you do pyrolysis or gasification, and this is where you talk, right, when you talk about the energy. So it means the decentralization of these processes are very, very important when you talk about the issues like parallel burning and all these things. Because the collection and segregation at one point, then convert it into something like high density material, I talked in terms of the right torrefied biomass, which you call biocoal, and then transfer it to refinery. So that kind, or the second option could be you convert this biomass into bio oil and transfer it to the refinery. Both options are possible. In both cases, all these terms are to be studied. That is the requirement. So you see that, right? If you do this, 30 tons carbon storage, 30% of the fixed carbon equivalent, which is 110 tons of the carbon dioxide emission, and that's why the government is saying that use the bio-based refineries and convert it into whatever the product you want. So your dried biomass 300 ton if you have, you can get around 120 tons biomass. 40% approximately is the conversion factor. And you have biochar, you have several. Now, whether it is hydrothermal or pyrogasifier or pyrolyzer or slurry waste reactor or fluidized bed reactor, this is the design, because the challenges are there. It looks the flow sheet simple, but tar is a big culprit compared to the coal gasification in the biomass, right? So whether it is plasma based, induction based, or some other heating material where this tar can be kept at its minimum, or you reform the tar, right? 800, 900 degrees centigrade, you can reform the tar, again you will have hydrogen and CO2. So this is where I think the opportunity, oxy, steam, water gas shift reaction, separation, purification, and then you can have again the bio oil, steam, oxygen, all those things can be reformed, you can have hydrogen. So they are one of the approaches for utilizing the bio oil. This is what we do, right? I am not going in detail. So we are looking forward to 1 ton of this biomass gasifier for hydrogen production. We call it BTH or XTH. So biomass plus RDF. So we are looking, right, support from MNRE and some other investors, industrial partners. So you see that in the UP itself there are 22 million ton of this biomass is available, right? And this is a huge amount of it. Per year you can get this, right? And RDF 68 million ton is already there, right? So those things are being done in terms of the development and gasification and all this for power generation. But these things, right, you see a typical flow sheet which can be used, and 1 kg of this, our analysis is that 15 kg biomass can give you 1 kg hydrogen, and that too at a rate of 150 rupees per kg hydrogen compared to 450 or 350 in the water electrolysis. So this is one of the methods. You cannot fulfill the complete demand, but partly green hydrogen can come from there, and this is where you can have a hydrogen compression, storage, or hydrogen plus biogas methane separated, and hydrogen plus methane, hythane, all these things are for vehicular application, for commercialization, it can be done. So another important area is sustainable aviation fuel. You know that now government or European government has already made a mandate for adding this, right, SAF, which is written there, SAF blending target. India has given 1% by 2047 and 5% by 2030. where from you will get this sustainable aviation. This is a substitute for kerosene jet fuels, aviation turbine fuels, all these things, right? And this is a green fuel. So whether it is from biomass to bio-oil and bio-oil to SAF, right? Or it can be from the CO2 also. CO2 to SAF is very, very challenging, right? We have just started electrochemical conversion of CO2 to SAF. So that's where but this is, right, the process. If you look at how it can be done, opportunities are there. Entire process you see, 1, 2, 3, which you see, reverse water gas, shift reaction, Fischer-Tropsch route, all of you know that. Methanol route, you convert it into methanol, convert to methanol and olefin and then hydrogenate, because it's nothing but hydrogenation, isomerization, cracking and hydroisomerization. Olefin, saturate olefin and get something C6 to C8 range of hydrocarbons, these are called C8 to C16 hydrocarbons, that is the SAF, right. So sustainable aviation fuel is the huge demand for the future when you look at this point, because Europeans will ban all these aircraft unless they have this, right, additive fuels which are green fuels. So this is also very important and emerging area. And you see the chemistry, you have to understand all these things, aromatics, isoalkanes, normal alkanes, and then how these can be obtained from this, right, a mixture, which is nothing but isomerization, isoparaffins are generally, you know, octane numbers and all these things, right. Olefins are undesired, so saturate the olefin, larger molecular weight hydrocarbon, right, their viscosity, pore point, all these things, freezing point will be challenged, so break them into a smaller one and isomerize it. Simple traditional refinery chemistry, right. So, but this is coming up again in a big way for the future. This is again the membrane, what I saw, e-fuels which are coming up, right. So membrane has a lot of challenges when you talk about electrocatalytic CO2 reduction, right. You have a cathode, you have an anode, I am not going in detail, but cathode material, anode material, then gas diffusion layer, everything is one step of the process. And integrate it and stack it. And that's what again, very, very important promising area for future when you talk about the green fuel, because the temperature requirement is just below 100 degrees centigrade, right? Unlike that 700, 800 degrees centigrade. Pressure requirement is also just atmospheric or 2-3 atmospheric. So all these things are required, but it looks like again a simple flow sheet, but if you look at, these are the challenges, right? Because at an economical prices, CO2 is to be converted to olefins for converting into SAF, or even when you talk about water splitting, there are a lot of oxygen generation which is called OER. All of you, those who are working in that area, that's right, they know this, but oxygen evolution rate is to be reduced, right. So OER, HER balance, and this gives you a lot of, when you see this, right, the challenges in terms of electrode, electrolyte, membrane and flow design. A lot of now CFD calculation, channel reactor design, that is required, but you see the flow design, last part. Electrode, you see the gas diffusion layer. Catalyst, electrolyte, liquid electrolyte, aqueous, non-aqueous, right, acid neutral, organic, membrane, right, cation exchange, anion exchange and bipolar. Everywhere there are a lot of opportunities to work for the future, and I think this is again very, very important, and circular economy is very, very important. Whether it is a solar cell you are talking, right, for energy generation, life cycle assessment, when the life is 15 years, or a battery, life is 15 years, where are you going to take it? So it means the waste to resource, I will not say waste, resource to energy or, right, recovery is very, very important, and that is also to be addressed in future. So this is what the challenge, right? All of you have to just work on the electronic structure engineering. So which kind of metals, right, support heteroatom doping, vacation creation, because, right, recombination rates and all these things are very, very challenging here. Vacation creation, S-sites, so defects are to be created. Same thing for the interface engineering, heterostructure support, right, single atom catalysis, that's important. Then super hydrophilic, right, super aerophobic. These are some of the areas, right, where I think new generation should take for the research. So these are the right technologies which are to be addressed when you talk about, so many areas. One person cannot do, one group cannot do, so multidisciplinary, multi-engineering, this is what the need of the hour, where we need to work in total when you talk about a combined, a module-based design for the membrane-based electrolyzer. And then stacking, because you have to talk about not 1 kilowatt scale, you have to talk about megawatt scale. Right? So a lot of industries are already working. If you have the ideas, if you have concept, you can just discuss with them, whether it is BHEL or NTPC or several other groups, right, who are working on this, IOCL, BPCL, HPCL, refineries, petrochemicals. They all are looking now substitute for the thermochemical also and working on the electrochemical approaches, because these are the challenges which are to be addressed, and only academicians can do this. Right? Which kind of catalyst stability, contaminant tolerance, right? So that is very, very important. Then mechanism, pH effects, channel design, humidification requirements, iron water membrane transport. So all these things are, again, I think we need to work in these areas. And this is what you see the module, right? Whether it is a kind of CCUS using membrane, so novel membrane based capture and conversion. So in a one pot tandem process. So because capturing and transporting CO2 to other process is also challenging. We don't recommend that. You capture it and convert it there itself, right? So this is also because transportation cost for carbon dioxide, whether you reduce, right, the pressure at high pressure, transport it, all these things, the material of construction, all these things become very, very challenging. So this is also at source and in situ if you can do, and all these things, right, combining membrane, functionalization, configuration, and this is where the electrochemical engineering is very, very important. All these things would be required. Just at the end, I thought that I would just give a comparative study why people talk photochemical, electrochemical. Region is this one. You see that the last point, 125 to 400, that is kilowatt hour per kg of the product. That is in terms of hydrogen, if you just look at, right, or CO2 conversion, if you look at. So versus this 35 to 100. So that's a much lower number when you talk about electrochemical or photochemical. So that's why the electrochemical catalysis, electrochemical process where you talk about e-methanol, e-ethanol, or where you talk about e-olefins or e-refineries. So those are very, very important, and maybe the future will be on the electrochemical conversion once the technologies, right, are developed to that level. So I think we need to look forward on all these things. So this is where the, right, digital twin all of you talk, right? So physical twin when you talk about operational stage, and then data twin when the, right, models are to be developed, data management, data analysis. So a lot of new things in terms of the role of artificial intelligence, real data analysis, because the data are available. If these data can be analyzed effectively, of course the right data is very, very important, ethics is very, very important, and that we need to work. And this is where, right, the refineries are looking in terms of steady state simulation, kinetic models, trade to trade distillation, because distillation is very, very costly, you find out the solution, and overall refinery optimization is nothing but in this closed loop, and we need to think in the terms where the refineries, petrochemicals and industries are looking forward. So this is where, right, low carbon and climate adaptability, so we have to work like this, process innovation and integration, so ideas are very, very important. CO2 if it is there, utilization is important, energy infrastructure is important, where the 6 to 7 gigawatt renewable power is required when you talk about refinery integration. Solar and wind would be, I think, one of the best options. Technological advancement, so novel technologies are required, global learning policy, so these things are also very important and we need to work on it. This is where I think the challenge, right? The academicians always, right, they think the research invention and publicize the paper, patent file, and they stop there. But I think the era is something like that when we talk about transformational, applied research. I think from fundamental to applied would be required, and either there should be a team, one work on fundamental and the team should take it to the next level, applied it, and this is, I think, TRL innovation where the industry's partners should be required, finally commercial market 89. This is very, very challenging, and most of the time what happens, we do the research, a lot of good work is being done, but they are kept on the file, papers, patents, but cannot be taken, right, to the next level because of several limitations. So policies are also very, very important. I think the government should also give a thought, industry should also come forward, and wherever the good work, wherever the technologies can be taken to the next level, I think the industries or government should support, and how the policies can be made. I think the Institute of Technology Development, the policy, right, formation is also very, very important. And where again the role of academician, industry and policymakers becomes very, very important. So finally to conclude, if you look at the future, right, we need to work on these areas. I'm not reading all these points, but this is what you see, the subsidy amount which is required, because the government has to support these processes, whether it is solar, wind or some new process. support which is required for 750 million ton per annum of carbon capture, whether it is utilized or stored, right, it comes around 210,000 crores. This is the data not taken by me. I have taken it from some of the ministry that Niti Aayog data, and 210 crores is the huge amount of investment. But this is required. We have to think in this way that where from this fund will come, and then the government should support, industry should support, and I think that would be the future where we need to look at the success of the entire technologies. So I close myself here. This is the work done by my team, part of this from IIT Delhi, and a new team from IIT Roorkee are yet to work. Some of the professors who are involved in this coal to methanol technology, so I kept their name also. Some of these students have now become the faculty or industry, they are already gone, because this is the slide which is in 2022. And this is the IIT Roorkee 𝗁𝗁𝘁 building called James 𝗁𝗁𝘁 College of Engineering earlier, and this building is James 𝗁𝗁𝘁 building, unique building, established in 1847 and 178 years old building now, and the facade and everything front, because of our alumni demand that it should be kept as it is, so we are maintaining this building as it is. So thank you very much for sparing your time, and thank you very much for giving me the opportunity. Any discussion, I would be happy. Yeah, sure.
Thank you, Professor Pant, for a very thought-provoking and stimulating lecture. I'm sure some of you have questions for Professor Pant. He has kindly agreed to answer those questions.
There is a thought process which suggests that crude oil or the fossils, they should not be used for energy, but they should be used for producing other chemicals, so on and so forth. From this point of view also, and from the point of view that for fossil fuels as well as for crude, we have to depend on other countries, what do you think about the nuclear way? We have abundant amount of thorium. I have been told that 1,000 years we should be able to consume that and support our nation for energy. So just want to hear your thoughts on that.
Yeah, this is very important, and already the pink hydrogen, the world which has come after this turquoise or blue hydrogen, this is from the nuclear. If you are able to generate hydrogen by using the nuclear source, then it is called a pink hydrogen. See, India is already now looking up, because somehow, because of the safety reasons, and the mindset, people were thinking that nuclear energy will be hazardous, more hazardous. But believe me, it is much less hazardous, because the amount of the nuclear sources which are being used is just less than 1% for achieving these kind of 500 gigawatt hour of energy. So this is a new area, and Niti Aayog has already energized this thing, that work on the nuclear energy, and academic institutes are required to work first, do look at kind of the feasibility, because all these power plants, which are coal based, can be replaced by this nuclear power plant, and that's what I think the work is being done. All the solar energy, which is being looked into, I think it has been made that solar energy plus partly nuclear energy, the refineries will also be asked in the future. And this is a very new area, but research is required, because we are looking forward something like the cobalt based, nuclear materials, nickel based nuclear material, not traditional like this radium, uranium, all those kind of. So those is also, again, if those are important areas for future. How can you generate those kind of nuclear, or tuning the isotopes which can have more and more energy, in terms of the process development. Yeah, this is a good area in fact.
Thank you, Professor, for a very interesting talk. I'm coming from a different background. I'm from management sciences, work on the policy side mostly. Generally what happens is whenever an idea originates, say, at some point it was a solar or then battery, and now it was green hydrogen. There is a lot of discussion which revolves around it. You have an excitement coming up. There is researchers which come forward to some extent, because like academic institution, they get involved into it. But sometimes the euphoria created becomes so big that government ends up committing a lot of money. Like for example, for green hydrogen, they're saying 50 rupees per kg or 40, 30, some 14,000 crore they are committing. But what has happened over the last 2-3 years, as far as with my limited knowledge, that if I can call it euphoria, has actually slowed down. It's not died down, but it has slowed down significantly. Even in the Western countries, they are rolling back their plans. Australia, UK, everywhere they are rolling back their plans. So what is it that is missing? Is it because the euphoria created was wrong? Is it because academia, because you cannot catch up immediately? Or perhaps the policy design was somewhere lacking something? And this happens more or less everything. You can see, you remember 𝗁𝗶𝗁, which was being taught biofuel at some point of time. Where are those plants? There is nothing there. It came and it went, which means somewhere the analysis was incomplete. The policy thought was really definitely not foolproof. We just ended up saying we will have millions of hectares of 𝗁𝗶𝗁, but there is not a single plant probably anywhere as of now. So your thoughts on that?
This is very, very important, right? And I will not answer the complete part. I will try to give some meticulous answer for this. See, one thing is clear, like you said, green hydrogen. I am sure that in the next 5 years, this is not going to come in success. So we are looking e-vehicles. So maybe in the next 5 years, still you will have e-vehicles. E-vehicles have the issues like lithium availability, people are working on sodium based also. But life cycle assessment when you do that, right, recovery of the metals and where are you going to dump these used e-vehicles and lot of issues in terms of, so policies have been made. But how these policies have been made in context to the Indian scenario, there are some lacking. So sometimes what happens, we copy the things directly from the Europe or US. But we have to think our own Indian scenario, public mindset, perceptions, resource availability, that's very important. So green hydrogen also, right, maybe Europe they are saying that they have produced at 200 rupees or 250 rupees per kg, but we are still struggling with 500 or 450 to 500 rupees per kg. So 400, 550, nobody is going to buy that right, hydrogen. Because 150 is also costly. Reliance saying $1, but you know how much time will it take to come to $1? That is out of question as of today. So it means sometimes we talk on big things, right? But execution wage, like you said, policies are being made, but the right persons to make the policies is challenging, right? Who is making those policies? We don't know. And sometimes they say that go to this fuel, but finally when you come to the ground level, it will observe that it is not practicable. So sometimes I think there is a need to work on those where the policy makers should involve others also, those who are involved in those kind of works. So I think that is required, and some work is already being done now. Say Ministry of Coal has prepared some database, and MOPNG is also preparing. Niti Aayog is doing lot of work in diversified areas, because the cradle to cradle approach is required nowadays, not the cradle to gate. So ultimately the e-vehicles, when it is being used, batteries when are they being recycled properly, resources being recovered, or these are dumped into some yards, right, and making a landfills, right? You see those examples. So we have to do cradle to cradle analysis. And for that, I think green hydrogen, which we are talking, that combination of hydrogen with other fuels like biofuels, hybrid systems will work, like hethane. Methane is there, 20% hydrogen is there, you crack methane, hydrogen plus methane, and you run the hydrogen CNG bus. That is being done. IOCL tested also, but not coming to the ground level because hydrogen is not available. Even that 20% hydrogen for vehicular application not available because industries are consuming huge amount of hydrogen. So that is a challenge. E-vehicles, that market is there, and that's why it is being envisaged that next 5 years will be for e-vehicles, and after that the green hydrogen. So it means the policies are to be regulated as per the need of the market. That's important.
Any other questions from the audience? Please.
There was a slide where you showed the conversion of biomass to bio-oil and then to a normal conventional fuel. So, but generally bio-oil is composed of several million oxygenated compounds belonging to different families like lignin, cellulose. And so there is no one particular catalyst or a route that can entirely upgrade that bio-oil to a normal conventional fuel. So in that case, how can we can say that the bio-oil can be used directly as a fuel in the coming future, because it's very difficult to catalytically upgrade. We can work on the model compounds present in the bio oil, but to completely make it usable into a transportation fuel is very difficult. So how can we come up with like a process or a catalyst that can completely convert it into a usable fuel?
Yeah, good question. Actually, a lot of work is being done and has been done also when you talk about, please sit down. So bio oil has a challenge in terms of its acidity, right? So your traditional catalysts, which are generally NIMOX based catalysts, which are used in hydro treatment, right? They get failed when you talk about the pH3, right? pH4, something like that. Zeolites and all this. So there is a tuning of the catalyst which is required, right? And little bit maybe novel metals. So when you see, right, a lot of papers are already there in this where you talk about the, one thing is that the deoxygenation of bio oil, because bio oil has a lot of oxygen and this oxygen is coming from phenol. So you have to give a high temperature treatment for removal of this. Or another option could be all these phenolic compounds, they have a lot of other commercial applications. You find a way by which it can be separated from there, phenolic compound, it gets separated, they have a lot of other traditional, right, petrochemical application and use this rest of the bio oil. So both approaches are being done. Hydrothermal liquefaction of this bio oil for hydrogen along with, because hydrogen will come in situ and simultaneously all these will be cracked and converted into respective hydrogen. So this is bio oil to SAF. This approach is being, we are testing mustard oil, bio oil, one of the projects. So mustard oil is available in plenty in Rajasthan area. So that mustard oil we are looking forward converting. Similarly, other bio oils can also be, and this is being done, right? So catalyst tuning can be done. You can have the right Bronsted versus Lewis acidity depending upon the isomerization which is required. So characterize it and accordingly set it. Right? So physical characterization of the bio oil and then you can design a catalyst.
Let's once again thank Professor Pant for
Thank
a
you
very
very much.
thought-provoking
Thank
lecture.
you.
I now request Professor Yogesh Joshi to kindly present the memento as a token of our appreciation. I request Professor Pant to be seated and I request Naveen to give the vote of thanks. So we come to the concluding section of this event and some acknowledgements are in order. So first and foremost, on behalf of the department, I would like to thank the donor, Mr. 𝗔𝗯𝘀𝘁𝗿 for funding this lecture series. And then, of course, big thanks to our speaker, Professor Pant, for accepting our invitation and delivering this wonderful lecture. I think it was a very short notice, and being a director, we understand that it was difficult to take this time out, but I'm just an acting head, still overwhelmed, so I can understand. Then I would like to thank the seminar committee led by Professor Shankar for organizing this seminar. Also, I would like to acknowledge the head of computer science department for allowing us to use this facility. Also thanks to CHE staff, especially Mr. 𝗔𝗀𝘀𝘁𝗿, who has been looking after all the logistics. And lastly, I would like to thank all of you for coming today for this lecture series. And this concludes this event. Thank you so much.